Okay, today we have Christian Carrick from Bonn University, and he will tell us about slice spectral sequence through synthetic spectra.
Okay, thanks, Guchuan, and thanks for the invitation to speak here. Um, okay, so let me get started with some motivation. So I'm going to talk about the slice spectral sequence, and I want to say a bit about where it comes from. Um, so this comes from the Hill-Hopkins-Ravenel solution to the Carrick invariant, um, which was motivated by earlier work of Ravenel on the odd primary version. So he proved an odd primary version of that result for primes greater than 3. And I want to just briefly review his strategy. So what he did was he looked at the following diagram of X groups. So here on the left, the map is the map from the Adams-Nabokov E2 page to the Adams E2 page, and the map on the right is something coming from formal group law data. So specifically, this is the height p-1 Morava E theory at the height p, where there's a CP subgroup of the Morava stabilizer group, and a CP action on that Lubin-Tate homotopy groups. And this map is just an algebraic thing coming from formal group laws. And okay, so his strategy was as follows. So the Carrick invariant classes were some classes on the E2 page of the Adams spectral sequence called theta J. And the question was whether they are permanent cycles in that spectral sequence. And what he showed is that if you take any lift, let's call it theta J tilde, along this map to the Adams-Nabokov E2 page, that this lift would support a differential. So he used a power operation on this BP star BP E2 page to prove that there was some differential d2 p-1 on any of these lifts. And a priori, he doesn't know that it is actually non-zero. And the way he proves that it is non-zero is by mapping it into the group cohomology, where you can see directly that it's non-zero because the thing on the right is much, much smaller than the thing in the middle. Okay, so this goes to non-zero in target, so it's non-zero up there. And then that means that none of these theta j tildes can be permanent, so then theta j can't be permanent either. Okay, and I guess the kind of notable feature of this is that it's a mostly algebraic argument. So we don't need to know, for example, that that this target over here is the E2 page of a spectral sequence, and in particular that this map here is coming from a map of spectral sequences. Okay, so Hill-Hopkins-Ravenel built on this argument at the prime 2, and there they did need more than just this algebraic data. So the kind of first thing they noticed is that you could lift this diagram to one of spectral sequences. So on the left, you have the usual map from the Adams-Nabokov to the atoms. And then on the right, you have a map from the Adams-Nabokov to the homotopy fixed point spectral sequence. And here they needed to use height 4 Morava E theory, which has a C8 action. And this, again, is more data than the approach of Ravenel, because you're using that this is actually a map of spectral sequences. Okay, and so as far as this approach goes, let me just make a remark that they knew before introducing the slice spectral sequence, they knew the detection theorem in the sense that they knew that any lift theta j tilde of theta j would be detected in this homotopy fixed point spectral sequence for E4C8. And the problem was that this spectral sequence here was not computable. So, but this homotopy fixed point spectral sequence was not feasible to compute. And so this is kind of one way of looking at where this slice spectral sequence comes from, or what problem it was introduced to solve. So the slice spectral sequence of their detection spectrum, omega, say was intended as a sort of connective model of this homotopy fixed point spectral sequence. So I'll say more about what I mean by connective model in a moment, but just briefly, the idea is that the reason that this spectral sequence here is so hard to compute is because it doesn't have any good vanishing lines on the E2 page or vanishing regions, and it's not finitely generated in each degree and all of that kind of stuff. And this slice spectral sequence will have those properties. Okay, so the first theorem I want to state today is kind of a gives some backing to this slogan a bit of the slice spectral sequence being a connective model. So let's take that first. So the first theorem is that there is a T structure on filtered G spectra. G is always going to be a finite group for me, such that for X at G spectrum, the slice filtration of the Borel completion of X is the connective cover of the homotopy fixed point spectral sequence. So first of all, I haven't told you what this T structure is yet, but I'm just calling it the slice T structure. And so this here means the connective cover in that T structure. And I also haven't explained yet how to implement the homotopy fixed point and the slice filtrations as things in filtered spectra. But for the moment, you can just imagine that they are some appropriate filtered spectra that give rise to those spectral sequences. Okay, and that's the statement of the theorem. So let me give one remark. So the one reason that I see this Borel completion here as kind of a bit harmless is because I have the following applications in mind. So if I take G to be a cyclic 2 group, I'm going to define this MUG as the norm from C2 to G of MUR, which is the real Bordism spectrum. And the remark is that this is Borel complete. So that means that MUG is equal to FEG plus MUG. So in this case, this FEG plus is not playing a role, doesn't matter. So there it says that actually the slice filtration of MUG is the connective cover of the homotopy fixed point filtration in this T structure. Okay, so I will say more soon about what this T structure is good for, but I want to, for the moment, say a bit more about what I mean by this being a connective model. So this T structure is kind of a sense in which it's a connective model, but more conceptually, this idea of connective models comes from the following analogy. So the slice filtration of MUG is to the Homotope fixed point filtration of MUG what the Adams-Novikov spectral sequence of little TMF is to the descent spectral sequence of big TMF. So the analogy here in the bottom row comes from the work of Hawkins-Mahowald, who observed that the descent spectral sequence for periodic TMF was a much busier and more complicated spectral sequence than the connective version. The connective version had good vanishing lines from the E2 page and was sparser. And their observation was that that made this computation for TMF much easier. And so this TMF is sort of the prototypical example of a connective model. And the slice spectral sequence is kind of participating in that analogy. Okay, and now with this kind of analogy in mind, one might wonder if the slice spectral sequence has something to do with an Adams-Novikov spectral sequence. So kind of one more curious observation in that direction is the following. One can compute directly that the slice spectral sequence for ATIA KR is isomorphic to the Adams-Novikov spectral sequence for KO. And so this, again, kind of leads one to ask if the slice spectral sequence is at all related to Adams-Novikov spectral sequences. And that's the kind of, just give me a moment here, this down. The next theorem I want to state here in this direction. So the theorem is that there is a lift of the slice filtration of MUG along the following forgetful functor. Okay, so I want to unpack what I've just written now, and I have this table here to help make sense of this a bit. So a kind of useful point of view on spectral sequences, which comes out of things like studying filtered spectra and synthetic spectra, is that it can be really useful to study filtrations instead of spectral sequences, in kind of the same way that one would study spectra instead of cohomology theories. And in this analogy, kind of some of the main players are the following. So first of all, in this analogy, a filtration means an object in filtered spectra, and that gives rise to a spectral sequence. And the idea is to try and work on this side of the table as much as possible, and then pass to spectral sequences sort of as late as possible. And so in this analogy, what MU synthetic spectra are filtrations which give rise to things that look like Adams-Novikov spectral sequences. So I think it's sometimes useful terminology to call such things modified Adams-Novikov spectral sequences. Okay, and in the filtered world, a map from the Adams-Novikov filtration of the sphere to a ring spectrum R in filtered spectra corresponds to or gives rise to a map of multiplicative spectral sequences from the Adams-Novikov of the sphere to the Tau-Bockstein of this filtered ring R. Okay, so I want to use this to unpack the theorem statement above a bit. One can also look at equivariant filtration, so that is filtered G spectra. And this turns out to be the same thing as G Mackey functors valued in filtered spectra. And so from that point of view, objects here are giving rise to spectral sequences of Mackey functors. And so then if I take G Mackey functors valued in MU synthetic spectra, I'm just sort of combining these two lines here. This corresponds to something like Mackey functor of modified Adams-Nabokov spectral sequences. Okay, so that's just a bit of unpacking. So now I can return to this theorem statement. So what I'm saying here is that the slice filtration of MUG is some commutative algebra in filtered spectra, and that structure refines to the structure of a commutative algebra in Mackey functors valued in MU synthetic spectra. Okay, and that would be a sort of statement appearing on the left side of this table. And so let me just state now the kind of concrete corollary of that, which would be the statement appearing on the right side of this table, is that there exists a map of multiplicative spectral sequences from the classical Adams-Nabokov spectral sequence to the slice spectral sequence of MUG. Okay, and the idea is that if you wanted to try and construct such a map directly, it's not so clear how you would do that, because this slice spectral sequence isn't coming from any kind of Adams spectral sequence construction. And so somehow working on this left side of the table gives you the tools to be able to still be able to construct a map like this, even if at the end of the day, all you wanted is this kind of concrete consequence. Okay. Are there any questions at the moment? No? Cool. Okay, so
are you saying, sorry.
Sorry, I have a question.
Can I ask first?
Go ahead.
You can go first.
So the existence of
Yes,
this
please.
map of spectral sequences are induced by the level of filtration. Is that what you're saying? Or
sorry, I didn't catch it full. I think your service cut out a
so
bit.
for the corollary, you said there exists a map of spectral sequences, right?
Yeah.
So I was wondering, because there exists a map at the level of filtrations, then that's why we have the map of spectral sequences. Is that the reason the existence of such map, or?
Okay, so I think the internet was a bit cutting out there, but I think I understood. The question is that yeah. So
I think this is purely for the internet reason.
okay, no problem. Yeah. So actually, the slice thing is a filtered G spectrum, and I want to take its fixed points to get a filtered spectrum, and then there's a map of filtered E infinity rings like this from something which implements the Adams-Nabokov spectral sequence to this. And yeah, basically to get the thing above, you kind of take pi star or pi star star.
Yeah, so I have a question about commutative algebra. When you say commutative algebra, do you mean
Just,
non-equinary?
yeah, I just mean in the classical sense, so not like an n infinity algebra or anything like that. Yeah, so no norms here yet. Yeah, so just ordinary E infinity rings. Yeah.
Okay,
Hi,
thanks.
Christian. I have a question.
Yeah, sure.
So how do you think about the Mackey functors in synthetic synthetic spectra? So is that
Yeah.
like several layers of synthetic spectra?
We'll have fixed points at each subgroup, and each of those fixed points will be an MU synthetic spectrum. So exactly, it would be a sort of diagram of MU synthetic spectra with restrictions and transfers and things like that.
Okay, so these are all the classical, like each layer is a classical synthetic MU synthetic spectrum.
Yeah.
Okay. Okay, thank you.
Yeah, so let me say just on that note that there are many many versions of what one might mean by equivariant synthetic spectra. And so this is kind of just one such version. You can do other things. But yeah, so that's why I use this notation, just to make it clear what it is. Okay, cool. Thanks for the question. So I will talk about this T structure mentioned in the theorems now. So the first thing I want to do is talk a bit about slice filtrations. So I will mean something pretty general by this, but I want to start first with the usual equivariant slice filtration. And I want to remind everyone of the definition of that. So, so first of all, this is due to Hill-Hopkins-Ravenel. Let me write that. But there's a nice kind of other way of looking at this due to Hill-Yarnell. And they notice that you can define the slice filtration in the following way. So if I have a G spectrum X, we say that this is slice greater than or equal to n if the geometric fixed points of X, which is a spectrum, has the following connectivity as a spectrum for all subgroups of G. So, so again, this is a spectrum, just an ordinary spectrum, and then this is connectivity with respect to the usual T structure on spectra, so with the homotopy groups T structure. Okay, and this definition tells you what slice n connective means for every n, and this defines a sequence of T structures on G spectra, which are sort of nested in an appropriate way to give rise to the slice tower. And first I want to just kind of generalize that idea slightly. So I will do the following. So let's fix I a symmetric monoidal poset. So I mean a poset in the usual sense with a symmetric monoidal structure as a category. And then C is a presentably symmetric monoidal infinity category. So that's just the setting I want to work in. And also, sorry, I want C to be stable. Okay, so in this setting, I want to define an I-indexed slice filtration on C consists of following data. So I want for each little I and big I, a T structure, Ci in C. So I'm referring to T structures by their categories of connective objects. So, I mean, there's a T structure and its connective objects is this subcategory Ci. And these T structures together should satisfy the following conditions. So if I is greater than or equal to J, in big I, Ci should be contained in Cj. The unit should be contained in the T structure C indexed at 0. So 0 means the unit in the symmetric monoidal category I. And finally, I want to know that if I take Ci and tensor it with Cj, this is always contained in Ci tensor J. Okay, so this is a definition of what I am calling an I-indexed slice filtration, and you can keep in mind I can be the integers with its usual ordering. That would be an example of symmetric monoidal poset. And the proposition I want to state about this is that given this data, there exists a T structure on the functor category from I op to C, which is compatible with the Day convolution. So this symmetric monoidal, this is a symmetric monoidal infinity category under Day convolution. And the T structure, there's a T structure on it that's compatible with that. That has the property that if I take the connective cover of some object in this category, so X is something in here, and I evaluate it at some little I in big I, this is just the connective cover with respect to the ith T structure of X evaluated at I. So the point is that something in here is like a diagram in C indexed by I, and if I evaluate that diagram at the little ith point, taking the connective cover of the diagram in this T structure, just takes the connective cover with respect to the ith T structure at that point. Okay, so let me give an example of this. So let's take C to be the category of spectra. I will be the integers with the usual ordering, and the symmetric monoidal structure is addition of integers. And then I take alpha to be a real number. And for an integer I take the ith T structure on spectra to be the one generated by the following sphere. So this notation here means I take that object, and then I take the smallest subcategory containing that object and closed under colimits and extensions. And that generates a T structure on the spectrum. Okay, and this I claim gives an I-indexed slice filtration on spectra in the sense above. And the point of this T structure I just defined is that, well, this gives a T structure now on filtered spectra. And if X is a filtered spectrum, I want to define the bi-graded homotopy groups of X. Pi, little x and little y are integers. And this would be pi x of big X, x plus y. So X is a diagram from Z to the spectra, and I can evaluate it at an integer like this. So that's what the superscript notation means here. So this, my definition of bigraded homotopy groups. And if I choose this grading, then X is connective in this T structure if and only if pi x, y, x vanishes for all y greater than alpha x. Okay, so there's a bit of unraveling to do here. And sorry, this should be an I here, not an N. But really the point here is just that since I have a bigrading, I can think of the homotopy groups as living in the XY plane. And the connectivity condition is just that if I look at those homotopy groups and I take the line y equals alpha x, connective things have everything concentrated on or below that line. And the value in having this T structure is, if I think about this table from before where I sort of am manipulating spectral sequences in this homotopical category, filtered spectra, taking the connective cover of a filtered spectrum there is sort of like taking that spectral sequence and artificially enforcing a vanishing line on the E2 page of y equals alpha x. And so that can be a very useful thing to do. One kind of upshot of this is that since this slice filtration is compatible with the monoidal structure, I know things like if I take the connective cover of a E infinity ring, I get another E infinity ring. And that will be useful for us. So, okay. Now that I have this defined, I can define the T structure I mentioned in the beginning. So I want to say that filtered G spectrum is connective in the sliced T structure. Well, I can take, for any subgroup H, I can take the geometric fixed points of this filtered spectrum pointwise, and of this filtered G spectrum pointwise, and that gives me a filtered spectrum here. And I want this to be connective in filtered spectra in the T structure with respect to the line of slope order of the group H minus 1. So I just, in this example before, told you how to make these T structures with respect to a line. And so I'm defining a T structure on filtered spectra in the same way that this definition of the equivariant slice filtration was given above, where I say what it means to be connective on each of the geometric fixed points. Okay, and if you have worked with the slice spectral sequence, you would know that they sort of have these vanishing lines on the E2 page, the slope order of the group minus 1, and so that's kind of where this number comes from. And while I'm here, I want to also mention one slightly related or closely related T structure that I will need, and then I will explain later why I need this. But I want to call something the O slice T structure if the following holds. So here I want this connectivity for all subgroups H and G for the slice T structure. And for the O slice T structure, I only ask this connectivity for all non-trivial subgroups H and G. Okay, so that's two different T structures on filtered G spectra. And I will need both of them, but they're both defined using geometric fixed points, like I just explained. Okay, great. So that's the slice T structure, and that's the one that I mentioned in the first theorem. And while I'm here, I want to mention one other T structure on filtered G spectra, which is defined by the following. So I want to say X is connected in the diagonal T structure if xi is greater than or equal to I in the standard G structure on a G spectra for all integers I. So G spectra has the standard T structure defined by the connectivity of the Mackey functor homotopy groups. And if I do this pointwise on a filtered G spectrum, I call that the diagonal T structure. Okay, and that's different than both of these T structures above. Okay, so let me just make a first remark to unpack this slice T structure a bit. So something you can check is that if you have a filtered G spectrum X, and you take the connective cover with respect to the slice T structure, and then you plug in an integer n, this just takes the nth slice cover of the nth G spectrum xn in X. So this Pn is the usual notation for the nth slice cover. So what I'm saying here is actually this T structure is not really something new. It's just the ordinary slice filtration just repackaged as a T structure on filtered objects. Okay, so this sort of definition in terms of lines of slope order of h-1 is actually just kind of repackaging the usual definition of the slice filtration. Okay, so let me just state one proposition about this T structure. So the slice T structure respects the G symmetric monoidal structure on filtered G spectra. So this category of filtered G spectra has more than just the structure of a symmetric monoidal category, but it also has norms in it. And the slice T structure respects those norms. So for example, if you take a G commutative monoid in here and you take the connective cover with respect to the slice T structure, you still get a G commutative monoid. And I also mentioned this O slice T structure, so let me state what we know about that. This T structure respects the O symmetric monoidal structure, where O is the n infinity operad generated by norms H to G, where H is non-trivial. Okay, so there's also a version of like G symmetric monoidal categories where you don't have all the norms, just have the norms indexed by a particular n infinity operad. And in that world, this O slice T structure is compatible with that structure. Okay, excuse me. All right, so I defined all these T structures, and one kind of direct consequence is I can make the following definitions. So let's fix now a G spectrum X. And I can do the following with the G spectrum X. Now I can define some of the filtrations I mentioned in the beginning. Excuse me. Okay, so I'm going to define the slice, the Whitehead, and the homotopy fixed point filtration of X. And these are all defined in more or less the same way. what I do is I first take the constant diagram at X, so the constant filtered spectrum. And then I take the connective cover of this with respect to some of the T structures I mentioned. So here I take the diagonal cover. And the homotopy fixed point filtration is the pointwise Borel completion of the Whitehead filtration. Okay, so it's not obvious from these definitions that these things implement the spectral sequences that I claimed they do, but they do. And that's kind of a nice exercise in unraveling these T structures. And the most useful aspect of this definition is that this functor associating a constant tower to a G spectrum is lacks G symmetric monoidal. So that means that if X has a E infinity ring structure or a G E infinity ring structure, then so does slice X, because it's a composite of lax G symmetric monoidal functors. Okay, and so that's again one advantage of this formalism, is you can see, directly that you're going to get a spectral sequence out of this that is a multiplicative spectral sequence, and maybe respects norms and other things like that. So kind of in that direction, let me finish this section with the remark, which is that I can take the category of modules in filtered G spectra over a slice of R, for R a GE infinity ring, and this is a G symmetric monoidal infinity category, which is a kind of category you can use as a synthetic category for slice spectral sequences. If you want, you already in this category have a lot of nice tools available that are available for synthetic spectra. Okay, and this remark is maybe not something that's due to me, but is maybe known by a lot of people who have looked into this kind of thing. And I am more interested in the MU synthetic aspects of the slice spectral sequence. So now I will get to that. Okay, so I'll talk now about these MU synthetic lifts that I mentioned at the beginning. And let me, let's see. Let me just state again the theorem that I mentioned in the introduction, which is that if I take the slice of the Borel completion of a G spectrum X, this is the connective cover of the homotopy fixed point spectral sequence in the slice T structure. And actually, this is also true if I use the O slice T structure. And this might not be so obvious from the definitions why they would give the same thing. But the point is that these two spectral sequences already agree on the underlying non-equivariant spectra. And so the kind of difference between them is concentrated at non-trivial groups. And so that's why these two things agree, more or less. Okay, let me give just a quick proof of this. So first of all, there's a map from out of the slice and the Whitehead filtration of X to something I call the mixed filtration. And the point is that these two things are defined by taking the connective cover of the same object with respect to different T structures. So what I can do is I can take those two T structures, those two categories of connective objects, and take their union. And that gives me a new T structure. And I can take the connective cover with respect to that T structure. And because there are inclusions of connective objects, I get arrows like this, which are kind of co-units of the adjunctions. Okay, and so this gives me a way of comparing the slice to the homotopy fixed point, because actually both of these arrows are equivalences on underlying spectra. So these are equivalences on underlying. So that tells me that when I apply Borel completion, that they become equivalences. So this gives me the following. So first I can map the slice into the Borel completion of the slice. And that's equivalent to the Borel completion of the homotopy of the Whitehead of X, because these maps are equivalences on Borel completion. And the Borel completion of this is the definition of the homotopy fixed point. Okay, and then this maps to the homotopy fixed point of FEG plus X, which is an equivalence. And this maps down to the slice of FEG plus X. Okay, and there is a map here by, again, coming from this diagram here. Okay, and then that gives me this map here. Okay, so what I've constructed now is a map from here to here. And to check that it's a connective cover, I just need to show that that map induces an equivalence on connective covers. And so let me just say the key input to checking that. You check that if I take the slice cover, the Borel completion of the slice cover, this is the same as the slice cover, the Borel completion. Okay, this follows straight from the definitions, and is kind of, it's easy to check, and then that's the proof of this. Okay, so I don't know, somehow there's not actually something so hard once you have this definition in place to check this theorem. Okay, now let me explain why this theorem is useful from my point of view. So let me bring in now the Adams-Novikov spectral sequence. Okay, so one way of implementing the Adams-Novikov spectral sequence as a filtered thing is to do this décalage construction. So what I do is I take the kind of MU cobar complex, I apply the Whitehead tower functor to it pointwise. That gives me a cosimplicial filtered spectrum. And then I take tote of that. Okay, so this is this décalage definition. And this gives me a commutative algebra filtered spectrum. Okay. And so the first thing I want to notice is that there's a way to map from the Adams-Novikov to homotopy fixed point spectral sequences. And I mentioned this at the beginning when I was talking about HHR, and the idea is more or less the same as what they had in mind. So let's let R be a G spectrum, a ring G spectrum. If the underlying spectrum of R is complex orientable, then there exists a map from the inflation of the Adams-Novikov to the homotopy fixed point filtration of R. This is a map in commutative algebras in filtered spectrum, filtered G spectrum. Okay. So the proof is actually pretty straightforward. So first I start with this thing. And so this is defined in terms of this totalization. And there's a sort of limit comparison map, which describes, a map between inflating this totalization or totalizing the inflation. So this sort of limit comparison map. Okay. And there's a map from that to kind of the thing I get by tensoring everywhere with R. Okay. And then there's a map to this from, I can take the totalization of the constant diagram at the white head of R. And this map is given by using all of the unit maps for MU. Okay, and then this is just white head of R. Okay, and then the kind of key observation is that this map is an equivalence on underline. And that is where we use the fact that R is complex orientable on the underline. And that fact says that the Adams-Novikov spectral sequence of R collapses onto the zero line. And if you sort of unravel that into this filtered setting, it actually tells you this map is an equivalence on underlying spectra. So that means that if I apply Borel completion, it's an equivalence. And then I can sort of reverse this arrow after Borel completing. And that gives me then a map here to the Borel completion of this Whitehead tower, which is the definition on the W fixed point R. Okay. Great. So in other words, if I wanted to give this talk about implementing the homotopy fixed point spectral sequence as a MU synthetic thing, then this would be the main theorem, because what I've constructed is a map from the Adams-Novikov filtration to the homotopy fixed point filtration. Okay, but I'm interested in mapping to the slice. And that's the whole point of introducing this T structure, is because now we have a map from the Adams-Novikov to the homotopy fixed points. And there's a map I discussed earlier from the slice of this, which is the connective cover. So to construct a map like this, I just need to check that this thing is connective in that T structure. And then by universal property of connective covers, I get the map I want. Okay, so that's kind of an easy approach to constructing this map. And yeah, let me just state that and then make some comments on it. Okay, so I'm going to state the theorem from the introduction now in slightly different language. There exists a map, this to here, in CALG filtered G spectra, where R has the same assumption above, where R is complex oriented on the underline. And the proof is just, I need to check that this thing has the right connectivity. But if I take the geometric fixed points of the inflation, geometric fixed points is always a left inverse to inflation. So this is just the ordinary Adams-Novikov. And this is connective in the T structure with respect to the line y equals x. That's a classical fact about the Adams-Novikov spectral sequence of the sphere, having this vanishing line of slope 1. Okay, and so the point is now that if H is a non-trivial subgroup, this implies that this is connective in the y equals order of h minus 1 x T structure. Okay, that means by definition that this inflated Adams-Novikov is connective in the O slice T structure. Okay, and then we're done because I remarked earlier that the connective cover of this in the O slice T structure is this. And I have a map like this already. So I just checked this is connective, so it factors through the connective cover. Okay, so let me make just one more remark to kind of tie some of these things together, and then I'll stop there. So something that you can check is that if you take modules in filtered spectra over this inflated Adams-Novikov filtration, this is equivalent to Mackey functors in MU synthetic spectra. So I mentioned this category at the beginning, and now I'm kind of tying that back in. Okay, so if you're not familiar with this inflation functor, you can more or less take this as the reason why this appeared. So this is a non-equivariant object, and this inflation puts it in basically as something with a trivial action. And its role in this story is essentially what appears in this remark. So I want to give the slice filtration this commutative algebra object structure in here. And that by this equivalence is equivalent to providing a map like this. And so that's what this theorem provides. And so again, as a corollary, using the fact that MUG is Borel complete, the slice spectral sequence of MUG gives me a commutative algebra object in this synthetic Mackey functor category. Okay, I think I will stop there.
Okay, yeah, let's thank great Christian for the great talk. Yeah. Okay. Yes, I guess we can stop the recording and start the questions section. Okay, so any questions?